I want to give you a quick overview tour of the chemistry of alkenes. In other videos, I'll take up the details of these reactions. First, here's what happens. First and foremost, when you think about chemistry of alkenes, I want you to think of addition. That pi bond can be broken and replaced by two sigma bonds. The group that attaches to those carbons can be identical or different. I'll show them as different here for a specific reason. I want you to notice that if the two things attaching to the carbons are different, they're two different orientations. A could be either on the left carbon or the right carbon. So there are two possible products. In addition, notice that we've just created two stereogenic centers. So in these addition reactions, there are two factors we need to consider. Regioselectivity, the position of A and B, and stereochemistry, whether it's R or S at each center that we create. Beyond addition, substitution is possible at the allylic position. When the allylic position has a hydrogen attached to it, as I've shown here, there are conditions that replace that hydrogen with bromine. So we have addition and substitution and cleavage. It's actually possible to break the alkene in two, breaking both the pi bond and the sigma bond of the alkene. This reaction leaves both carbons doubly bonded, but to oxygen. It's like you took a pair of tiny scissors and cut the double bond. So here are the key transformations that alkenes undergo. Let's take a quick look at how these happen. First, take a look at the pi bond of an alkene. We'll turn it on its edge so the plane of the atoms is perpendicular to the screen. Now we can look at these p orbitals that are on the carbons and the region in which they overlap. This drawing is intended to point out that the pi bond has a lot of electron density above and below the plane, readily accessible to things that are attracted to electrons, negative charge. In addition, it's possible to break the pi bond of the alkene and not the sigma bond. This pi bond is electron rich, it's relatively weak, and therefore it can be broken by reagents that are electron deficient, reagents that are attracted to electrons. This leads to reactions with electrophiles. Reagents that need a pair of electrons to have a filled outer shell react with the pair of pi electrons in the pi bond. This carbocation, of course, is unstable, reactive, so it's an intermediate in the process that makes addition products. Alternatively, the pi electrons in an alkene can react with a metal surface. The initial product is a complex with the metal. This activates the pi bond and leads to addition chemistry. In particular, it's important in the addition of two hydrogen atoms. When alkenes react with radicals, there's two very different ways that can happen. One is like the reaction with electrophiles I've drawn up above. A radical has an unpaired electron. It needs one more for a filled outer shell. So the pi bond breaks using one of those pi electrons to form a bond, together with the radical electron. This leaves one other electron of the pi bond on carbon. This is an unstable reactive intermediate and goes on to form products. The other type of reaction with radicals is substitution at the allylic position. One of the two electrons in this sigma bond goes with hydrogen to form a bond with the radical. The other one stays on the carbon. Like the radical above, this is an unstable intermediate and goes on to form other products. In other videos, I'll talk about the details of these reactions. For now, keep in mind that the alkene double bond activates the molecule toward reaction. The pi bond is electron rich, so it reacts with electrophiles, and the main reaction is addition. Other reactions can involve substitution and cleavage.